Hey guys, it's February 24th, 2026. I'm going to do a tech talk, a deep dive into some source code like a Python talk. Like, imagine this is a Python conference and you have showed up with your laptop and you're curious about it, but you're not like, I'm not going to assume that you have lots of experience. I'm just going to give you an overview, but you might be coming to this already fairly well versed in this geometry that I'm looking at on this channel all the time, which is, volumetric. I'm going to scroll down here real quick and show you what the problem was. So there's a tetrahedron, right? Maybe it doesn't look that much like one. I'll just make it a little bit smaller. I use Vivaldi browser. I've got the slider in the lower right where I can resize, which is kind of cool. So that's like an XYZ Cartesian sort of box inside of which is floating centered at the origin, which is 0, 0, 0. So if you've got your high school Cartesian coordinates under your belt, we're doing these, but we wanted to send them on. The pipeline here is 3D print them. We want to 3D print these at the end of the day. Now that's very doable if your polyhedron's already omnitriangulated, which the ones I've just showed you are, but I didn't have omnitriangulated versions of, say, the cube, which is here now showing that has had face diagonals added on by software. So the goal was flesh out my existing software to allow omnitriangulation. So add the missing diagonals when your faces are not omnitriangulated. So how do we do that? And so how do we do that? I'm just going to first, before I really answer the question, we have to get into the overall framework. What is the picture here? I've switched windows. I'm on a Mac, by the way. What we're looking here is looking at is flextegrity py. This is Python code. Now all this writing in green is just notes. And you can have these things called doc strings at the beginning of certain constructions. By construction, the module itself, like this whole text file top to bottom, it's considered normal and best practice to put a big fat text stream or a text blob, a triple quoted text string at the very top of any Python module so that your reader, be that human or not, has information at the top as to what's going down. What is this? What is this that's coming up? And also keep a chronology, perhaps. This is what I do, usually, often, not always. Show when you've changed things, added things, and I've just been working on this omnitriangulation problem. That's partly why I'm doing the video now, so that it's when it's still fresh in my thoughts. But what's going on in this whole module? Well, basically, we're using what are called quadre coordinates to inventory what we call the major polyhedra or I sometimes use the word can't say this very well. Matryoshka dolls. Did I say that right? Matryoshka dolls, like the Russian dolls, throughout that region of the world. They make these like concentric dolls, one inside another. And it's not the best analogy in the world, but it's kind of what we're doing. We're nesting polyhedras one inside another in a certain way. So polyhedrons, a very good thing to learn on because they're very simple and we have them in common. We know what they are. We got the tetrahedron, for example. So what I do in this particular piece of Python code is I define what's called a class polyhedron. Now, what's a class? A class is like a cookie cutter. It's like every polyhedron internally to it. If you think of it as some kind of like organ or organelle, it has capabilities, behaviors, And these are triggered. Inside of the polyhedron, we have the actions that it can do. What can it do? It can scale itself, get bigger or smaller. Actually, when you scale something, like say you've got a tetrahedron, you say, make me bigger, you get back a new tetrahedron. It's not like it changes in place. It's like based on where we are right now with this tetrahedron, scale it up or down, shrink it or grow it. And that means all the corners, all the vertices either have to get further apart because it's getting bigger, or squeeze things down more tightly. And that means things are getting smaller. So there's a scale factor involved. So this is a cookie cutter method at the top level, like at the umbrella level, where every polyhedron is going to be able to scale itself. Every polyhedron is going to be able to move around in space without rotating, just translating. This is the graphics terminology of computer graphics and geometry in general. Any polyhedron floating in space can be scaled, which means made bigger or smaller without changing its shape. Translated, which means sliding around, no longer scaling, keep the same scale, but slide around, you're translating. And you can also rotate and picture that happening in place too. Now you can do all three at once and so on, but those are the three basic transforms. Now what's this distill? See, this is what I needed to mess with. And I'm not going to go into too excruciating detail, but what I added as a feature here is this little, we call it a flag or a toggle. And now when you initialize a polyhedron, you say, give me a new cube. You're going to be able to say whether this thing called omni should be true or not. By default, it's going to be false. But we might want it to be true. And if we pass in true when we initialize a cube, for example, and let me just show you what that looks like from the outside. So this is the code. This is like you could say backstage. But what it looks like from the outside is when we create a cube, first of all, we just import it from the Flextegrity library where all these polyhedra hang out. That's the source code we were just looking at. And there I'm instantiating a cube. I'm calling cube and I'm passing in true. So calling means you've got parentheses right after, kind of like a mouth that's eating something. We call the eating things arguments. You feed it arguments. I feed it true. Okay, so back to the source code. When I feed it true, it like comes in under initialization. And you're like, wait a minute, this isn't making sense already because this is called class polyhedron. And what we just saw there was a cube actually being born. I was instantiating a cube. So how is it calling polyhedron when I'm saying cube? That's already a deep question. No worries if that wasn't your question, but I'm using that as like, okay, that could be what is going on, and I'm going to show you down here in the source code, already line 364. So I just skipped over a bunch of stuff. Here's my first actual polyhedron. So there's these super umbrella term, polyhedra, class polyhedron, that's like the uber manager of the polyhedron type. But then there's a subtype of that. So when I say a subtype, I pass polyhedron, yes, it's an argument, to a class construct. I'm building the cookie cutter now for any tetrahedron, which means it's going to start out as this kind of canonical default tetrahedron. Already very opinionated, we say in the trade. All my polyhedra know how they fit together in this Russian doll's concentric hierarchy template. So they're already organized in a certain way. They already have default colors. And what's key, okay, this is going to be the key to the whole thing, is they all have these faces. So what you want to think of is like a sea urchin. Think of all these spokes, like really sharp now, all these arrows, all these spokes coming out of the common origin, something very prickly. Think of a prickly sea urchin, right? And you're not going to ever need all the spokes, probably, unless you're doing some kind of almost a sphere. but you just like pick certain spokes to get a cube. Oh, I'm going to need this, you name the spokes you're going to use. So this framework comes with a canned set of spokes. They're all expressed in what we call quadre coordinates, and they are just there and available. And based on those, I create what I call the faces, which are like a sequential mention of do this spoke, then this spoke, do A, B, and C. And at C, it's understood that we wrap around and we close off the face. So this is going corner to corner. Imagine a triangle. We go from A to B, B to C, and at C we go back to A. So we have a triangle with these 3 points. In other words, all of these lists or tuples, more technically, of letters or of corners are understood to loop around. They're like you're hopping around a fenced inner area. By a polyhedron, we mean all these fenced areas that adjut each other, are adjacent, share edges, share fences. And we have like a planet that's been carved up into fields. Think of a grass planet where nothing there is it's flat, it's a grass desert, and there's cows, and we care whose cows are whose, so we divide the whole planet up with fences. That's kind of the beginning of a polyhedron, right? On a spherical surface. Now, polyhedrons usually are presented as, straight edged and all this. Now, here's finally the cube. And what you see here is there's the cube face, A, F, C, H. Again, these are spokes in the sea urchin already have names. We just have to refer to them and describe the faces. Now, what happens with all of these polyhedra? They end in their initialization. So dunder init, where we go double underline init, that's where we start the cube. Like this is giving birth to, like as the cube is coming into existence, we get this like self comes from the Python itself, the mother. The mothership gives us this self, this polyhedron, a cube actually, that we then do sort of post-production. We shape it, we give it sort of some initial out-of-the-factory paint job, you could say. And then at the very last, we call up to the polyhedron. That's what we mean by super here. And we say, okay, now run the initialization up there in the polyhedron. Higher up, we think of. Like polyhedron's accessible to cube because cube is like an ancestor of or polyhedron's an ancestor of the cube. So I'm scrolling all the way back up to the polyhedron code. And I'm saying, okay, once we do the production work and create a new cube, then we come up here to the init they all share. Every polyhedron is going to have this last step. And you're going to check that omni and see if it's true. And if it is, we need to create some new faces. Because that cube I just passed in, you saw, it was all squares. But for 3D printing, we're going to need all triangles. So we're going to have to do something different when we distill. And this is the last section of basically what goes on that I'm going to explain here. You're learning Python. I hope it's interesting. What we do in distill is we get the edges. So think of a polyhedron, right? You've got these fenced areas. You've got these faces. But really, it's the fences to get this whole thing out there and on the screen or 3D printed or whatever. It's the lines, segments between the fence corners, basically. Those are the edges. And we've got the faces. We've already labeled the spokes that we're going to be using. So A, F, C, G, whatever, those are going to be a face. So those get us to the tips of these spokes. We know where out there in space we are with this thing, and we just need to distill the edges from there. We can use the face and just go around the face and go, oh, from here to here's an edge, from here to here's an edge. Like if we have the face, we can just get the edges from the face is what this distill method's about. We don't make the user define the edges. The user I should say the user in this case is just the polyhedron itself, the cube. As it's being created, as a last step, it throws its own faces into this distillery and gets the edges back. And that's what the logic here is all about. It's just about creating edge objects. Just like a polyhedron's an object, an edge is an object, a vertex is an object. In Python, everything's an object. But what is the wrinkle? The wrinkle is when we do distilling, we have to decide if we are going to need to use this omni method or not. And so where do I check that? Right here. If the omni that says omni triangulate, when you create that cube, remember back in the, go back there to this other screen, when we create the rhombic dodecahedron, the rhombic tricontahedron, those all have rhombic faces. Even a square is a rhombus. So in order to draw them, I had to omni-triangulate them first. There's the rhombic dodecahedron, and here's the rhombic tricontahedron. For these to come out successfully, the algorithm required omni-triangulated meshes, something that comes from the 3D printer format. I had to install this whole NumPy STL to get this mesh object that I could use. And the way I figured that out is here's where AI comes in. I actually did ask Perplexity, hey, I've got this problem. I've got the XYZ coordinates, and I need to create a 3D printer file. What do I do? And it came back with, a really good work plan, what I needed to do, what I needed to have. I needed to go with NumPy, and it gave me two different kind of, if you have the vertices, you're ready to go. Maybe you've got something more like a cloud. So it had even more complexity than I needed. And then, so I installed this thing. Anaconda has all this library. That's where I get my stuff in the cloud, is from Anaconda. Any modern language, it's going to have this cloud component where you don't have everything right out of the box. You're going to add to your inventory of software just by installation. So I take my reader through that in my write-up of this of this printing project here. What we've been looking at, I take my reader, I should say, all the way from getting this advice from Perplexity, installing the necessary package, and then massaging some code that depends on already omni-triangulated data coming from each polyhedron. This code was partly helped. I got a lot of help from AI to just get the boilerplate there. When I would have used other resources in the past to get, AI sure did make it faster to develop. I'm sure that's true. So in Omni, this is the last part. This is where you need to omni-triangulate or do the work of omni-triangulating. If it's true that we need to omni-triangulate, then when we pull up the faces, which we're already going to have at this point, because this is the last birth canal sort of moment, we already have all the faces for, say, a cube. If the length of the face, if it's only 3 points, and that's as few as you can have to have a face, then don't bother, just pass it on through, in other words. If it's just a 3-point face, if it's a triangle, you're done. But if it's more than that, then what we're going to do is break that face by picking an anchor point, the first point, and doing a triangle involving the next 2 points, and then come back to the starting point. There's your first triangle. Now pick up where you left off, pick off another new point, and go back to your anchor point. Same one each time. It's kind of like fanning out from a point and creating triangles out of whatever you're looking out on. A cube, easy, divided into 2 triangles. What about a pentagon? You'll divide that into 3 triangles, and I do have that as an example. Actually, let's do that as my final thing. Let's be in Jupyter Notebook and realize I forgot or don't have or could use a pentagonal dodecahedron. So I'm going to go to my source code here, and I'm going to say, hey, after the rhombic dodecahedron, I'd like a pentagonal dodecahedron. And true, I do need that omnitriangulated. Okay, so I'm gonna ask for that, and so enter the code there, rerun the code, and it says, well, that's not defined. I don't know what you mean by PD. How am I going to make a PD? Well, that's because I didn't import it from Flextegrity. Flextegrity, the source code we've been looking at. So if I scroll down again to the polys, you'll see there's the polyhedron cube, cuboid, octahedron. So each one has its own initialization, default color, and compute the vertices. You're going to say, wait, I remember this is all in quadrats. Why are you saying you have the XYZ coordinates? Well, in the final analysis, when I create these STL files, I will convert to XYZ files, to XYZ coordinates. That's part of a built-in ability of any quadrate object, is to output its corresponding XYZ coordinates. So here's the A module and so on. What did I do? Did I skip the pentagonal dodecahedron? It's got to be here. RT, scrolling up again, there we go. PD. And I had to do a lot of like vector algebra or vector initialization of a pentagonal dodecahedron took some thinking about, but that work's all done now, so I'm going to have to do it again. So I've imported PD now, and let's make this a little bit bigger for you. And now let's actually, okay, so there's a star there, which means it's thinking about it. You know, I just added something new. Let's see if it can figure it out. Why does it take this long? Maybe it needs to do some recompiling and something like that. I think we can come back to it and see if it's finished in a minute. And I'm going to scroll way down to, or I'm going to insert a new code cell by going plus, and I'm going to go plot shape PD. So when it's ready, I can then look at it. I can make it happen. So are we done? Yes, 18. So we're done. Scroll back down to where I'm locked and loaded. Let's check it out. Plot the shape. So this is going to run code that takes advantage of the fact that this thing's already omnitriangulated. By the time we get to here, that whole giving birth, that whole init part, that happens right away the moment you create one of these things. The moment I call RD with the true parameter, all that initialization I was just talking about, distilling, all that stuff happens lightning fast. I now have a RD lowercase or PD lowercase, my choice of names, object, and it's got all that internally. It knows basically what its own faces and vertices are and edges. It's computed its edges. So that's enough to create the STL file on the fly and plot it, and we'll end with this as the grand finale, a pentagonal dodecahedron. I haven't done this before, so again, I don't know how, it shouldn't really take a long time, but given the fact that I have a lot of stuff open on this poor little Mac Pro, and I'm doing recording, and I have my video editing software open, it could be that there's just memory issues too, but there we go. And you can see there is a pentagon, how it's been fenced into 3 triangles going around. You can, with your eye, you can see the pentagons, and then the 3 triangles that make up each pentagon are flat to each other. So it's like, that's why I didn't have them originally, because in a kind of textbooky sense, those extra fences are gratuitous, but not if you're thinking in a structural architectural sense. You need to stabilize this thing anyway if you're going to actually make it in a wireframe form. And that's why STL files and 3D printer files would expect omnitriangulation, because they're aiming for actual existence, not spooky metaphysics. All right, hope that was fun. Lots of Python there. Talk to you soon.